All right, good morning everyone. So I welcome you all on YouTube channel of Unacademy IIT JAM Live. This is Srishti and I teach live on Unacademy Plus platform. So today in this particular session we'll be discussing questions on molecular orbital theory. Basically we'll put more focus on homodiatomic molecular orbital questions, and for heterodiatomic molecular orbital questions and polyatomic questions you have to put more focus on theory, which we have covered already on Plus platform. So basically we'll have more questions on homodiatomic because 90% of the questions from molecular orbital theory in IIT JAM level are coming from straight from your molecular orbital theory of homodiatomic molecules. Okay, so I hope my voice is clear and you can hear me properly. Right, very good morning to all of you. So let's start with today's session. So let's take first question in front of your screen, and it's pretty straightforward question. Which of the following is true statement? Okay, you have four options right there in front of your screen. You have to tell me true statement. Good morning, Lovely. Good morning, Shruti. Good morning, Sandra. Good morning, Rajendra. Good morning, Sureka, Sambhav, Dhani. So this is the first question. You need to tell the correct answer, and it's very simple question. Okay, so I hope you all will get this question correct. Yeah, you can give your answers in the comment section. Okay. Yeah, so most of you are going with option A, and that is absolutely correct. So basically, you need to tell the correct statement. Yes, definitely, bond order is directly proportional to bond energy, right? Let's suppose I have three bonds, and bond between A and A is 1. Okay, bond order is 2 over here, and bond order is 3 over here, right? So if bond order is increasing in this particular order, what I'll say that I need to give more energy to break these bonds. Okay, because bond order is increasing, bond strength is increasing. If bond strength is increasing, that means I need to give more energy to break third bond. Okay, this one, right? So definitely bond order is directly proportional to bond energy, right? And it's inversely proportional to bond length, because if you are increasing the bond order, that means you're decreasing the bond length. Okay, so A is your correct answer over here. Right, let's take next question now, and it's match the following. You need to match out the options. Okay, you have column 1 and column 2. See, if you're clear with basic theory, so all questions are very simple. Okay, you can definitely solve these questions. There's no chance of getting negative marks in molecular orbital theory if your basics are good. Okay, if you have spent enough time on reading these basics, so these questions are very simple. Okay, all right. So most of you are going with option C. Let's see. See, in first case, is it constructive interference or destructive interference? See, these two are in same phase. Okay, these two are in same phase. So what we can say? This one is constructive interference. Okay, and this is d orbital and this is d orbital, right? And this is head to head overlapping. Okay, one lobe interaction. So whenever you have one lobe interaction, in that particular case there's a formation of sigma bond. Okay, so let's see in which option you have this answer, D and D sigma bonding. Okay, D and D sigma bonding, that means for A option 2 is correct. Okay, so you can go with option C. Let's find out rest of the options. So in this particular case, this one is p orbital and this one is d orbital. Okay, it's two lobe interaction. You can see it's constructive overlapping. It's two lobe interaction, so you'll get formation of pi bond. Okay, so it's p d pi bonding. Okay, it's p d pi bonding. So for B it's third. Okay, for C, in this case, it's constructive, it's destructive overlapping. Okay, see, these are out of phases, so it's destructive overlapping, and this one is also destructive overlapping. Okay, but it's two lobe interaction. So whenever you have two lobe interaction, so either you can get pi or you can get pi star. Okay, it's destructive overlapping, so that means it's pi star. Okay, so what you can see, it's p d pi anti bonding. Okay, it's p d pi antibonding, and you have first for option C. Okay, next you have option D, and it's one lobe interaction. So whenever you have one lobe interaction, you'll be getting sigma or sigma star, but this one is destructive overlapping, so what I can say, D D sigma antibonding, right? D D sigma antibonding. Good work, guys. So correct answer is option number C. Okay, great. Let's take next question now. So this is your next question. During the change of O2 to O2 minus, the incoming electron goes to which orbital? You need to find out that orbital in which the incoming electron goes when I just change O2 to O2 minus. Okay, so most of you are going with option B. Let's see. Now, during the change of O2 to O2 minus, okay. See, in O2, we don't have sp mixing, so molecular orbital diagram is like this, okay. You have first sigma bond, then you have pi bond, okay. Then you have pi star bond, then you have sigma star bond. So basically, it's a SOMO case, okay. This is how these electrons are filled, okay. So when you go from O2 to O2 minus, okay, so incoming electron goes to your pi star. Okay, incoming electron goes to your pi star. It can be 2px or 2py, but in this option, in this question, you have only one option from pi star. Okay, so B option is absolutely correct for this question. Good work. Okay, let's take next question now, and this is your next question. So questions are very simple for molecular orbital theory in JAM level, so just keep revising your notes which we have covered in plus platform. Okay, and all questions will be very simple. Okay, I think there is some mistake in these options. Okay, you can just ignore these options and you can give your answer. Okay, Just ignore these options and give your answer. Okay, just find out the most possible answers for these codes. Okay, right, so just ignore these options, Shruti, and give your answers. Okay. Okay, let's do for B2. Let's start for B2. Okay, so basically in B2, do we have SP mixing in B2? Definitely in B2, SP mixing is there. Okay, so how we have to draw this diagram? We can draw this diagram like pi, sigma, then you have pi star and sigma star. Okay, how many electrons we have to fill in p orbital? We have to fill 2 electrons. Okay, because boron is 2p1. Right, boron is 2p1, so we are only taking p orbital, so we need to fill 2 electrons like this. Okay, like this we need to fill these 2 electrons, so it's paramagnetic in nature. Definitely B2 is paramagnetic in nature. Okay, so for B2 we can write P. Okay, now tell me which is next correct option, undergoes oxidation or undergoes reduction. Can anyone tell me it undergoes oxidation or reduction? Which is correct, oxidation or reduction? Yeah, it's a lengthy question, so let's do right. Let's do this question. So undergoes oxidation or reduction, can you tell me which is most correct option for this B2, Q or R? See, you need to see electrons in molecular orbital. These electrons in are in bonding molecular orbital, right? So when electrons are in bonding molecular orbital, that means it's not possible for you to eliminate these electrons, okay? Because this will give you a decrease in bond order. So that's not possible. It's not a favorable process. So what I'll say, that definitely we can add electrons, right? We can add electrons in bonding molecular orbital, right? So it undergoes reduction, right? It undergoes reduction because, yeah, definitely, because they are in bonding molecular orbital, so you can add more electrons, right? You can say that there's a possibility of addition of electrons, right? So there's not a possibility of addition of this removal of electrons, but yes, you can add it. Okay, so we can go for our option also, right? Then your bond order is greater than 2, so it's 0.5 and 0.5. Okay, so definitely bond order is not greater than 2. What's bond order for B2? What is bond order for B2? Okay, can I say it's half pi plus half pi? Can I say that it's half pi plus half pi? Right? Because you have two electrons in these pi orbitals. Okay, so what I can say, that it's half pi and half pi. Okay, so basically it's not greater than 2, so you cannot write S for A. Okay, next is mixing of S and P orbital. Okay, so definitely there is mixing of S and P orbital, so PRT, right? PRT. So let's do this for N2. N2 is diamagnetic, okay, because this is how we can fill electrons in N2. 1, 2, 3, 4, 5, 6. Okay, N2 is diamagnetic, so it's not paramagnetic. Undergoes oxidation, it's not possible because you have electrons in antibond in bonding, so this is also not possible. Undergoes reduction, this is also not possible because you have to add electrons in antibonding. Okay, so that's not possible. Bond order is greater than 2, yes, bond order is 3 for N2, so yes, we have S for N2. Okay, mixing of S and P orbitals, yes, there is mixing of S and P orbitals. Am I clear? Is it clear for N2? All of you are clear, S and T? Just first confirm it in comment section. S and T are clear to all of you, that how we got S and T for N2, right? Okay, great. So let's do for O2 minus. It's paramagnetic. Yes, O2 minus is paramagnetic because this is your HOMO 1 and 2. Now you have added one more electron, that is, it's like paramagnetic. Okay, you have one right, unpaired electron. So yes, it's paramagnetic. Next is undergoes oxidation. Yes, you can do that, right? Because you have to eliminate electrons from antibonding. It's a favorable process, right? It will increase the strength of bond. So yes, this one is also possible. Okay, undergoes reduction, this is not possible because you have to add electrons in antibonding, right? You have to add electrons in antibonding, that's not possible. Okay, bond order is greater than 2, bond order is not greater than 2 because for O2 bond order is 2. Okay, so if you are adding one more electron, right, to O2 minus, what will happen? Bond order will get reduced by 0.5. So bond order will be 1.5 for O2 minus. Okay, it's not 2. So you can't write S for O2 minus. Okay, mixing of S and P orbitals. No, it's not possible for oxygen to mix S and P orbitals. Okay, so only P and Q are possible for C. Okay, let's go for option D, that is O2. This one is paramagnetic for sure. So you can write down P. Okay, undergoes oxidation. Yes, it can go under. Yes, it can go oxidation because you have electrons in anti-bonding. Okay, so you can write Q over here. Reduction is not possible. Bond order is greater than or equals to 2. Yes, bond order is 2, so you can write down S, right? And there is no sp mixing in O2. Is it clear to all of you? These all options are clear. Any doubts to anyone? Okay, just let me know if these options are clear to you, right? If you have any doubts in this question, you can definitely ask in the comment section. Okay, great. All right, so let's move forward then. This is the next question. Which one of the following properties is not shown by NO? Okay, it's MSQ question, right? So you need to tell the correct options. Which one of the following properties is not shown by NO, right? So it's MSQ question. You have to tell the correct answer. Yes, okay. It is diamagnetic in gaseous state. So let's solve for NO. Basically, you need to know how we can draw this molecular orbital diagram. Okay, let's draw for NO. So you have nitrogen 2p over here, okay, and oxygen 2p over here, right? Then you have nitrogen 2s, and then you have oxygen 2s. Okay, so what we need to understand over here, that there is sp mixing in nitrogen. Okay, so what will happen, you will be getting two hybridized orbitals like this. Okay, sp and sp dash. Okay, due to sp mixing, you will be getting two hybridized orbitals over here, sp and sp dash. Okay, now what will happen? Okay, this is going to mix with this orbital, right? This is going to mix with this orbital and it will form first sigma bond. Okay, then you will be getting sigma star, sigma and sigma star. Okay, then two pi bonds over here like this and two pi star. Okay, two pi bonds and two pi star. Okay, then what is left? One non-bonding is left. Okay, basically one non-bonding is left over here, right? So it will just go with this. Okay, so this non-bonding is left, and that's how you can draw this particular molecular orbital diagram. Okay, I hope all of you are clear with this diagram and you have revised it also. So this is a molecular orbital diagram for NO. So how many electrons we have to fill for nitrogen, right? How many electrons we have to fill? Anyone? Basically, we have to fill how many electrons? So you have one lone pair over here and you have one electron over here, right? So what we can say, that we have one electron over here and one lone pair. Okay, so it is diamagnetic in nature. It's not diamagnetic due to presence of one unpaired electron. It's paramagnetic in nature. Okay, it's paramagnetic in nature. You only have to consider frontier orbitals, right? So this one is paramagnetic in nature. Okay, so next is, it is neutral oxide. Yes, NO is neutral oxide. Okay, this is correct statement. It combines with oxygen to form nitrogen dioxide. Yes, it can combine with this oxygen to form nitrogen dioxide. Okay, that is possible over here, right? Its bond order is 2.5. Yes, NO bond order is 2.5. Okay, that's how we have to solve this question, and correct answer is option number A, right, which is the incorrect option over here, right? I hope it's clear. Let's go to the next question now, and this is your next question. Although it's a question from organometallics, but we have covered this portion also in molecular orbital theory, and you have to apply the concepts of molecular orbital theory only, right? So we can solve this question with our concepts of molecular orbital theory. Okay, the binding modes of NO in 18 electron compounds. So basically these two compounds are 18 electron systems, and we have to tell the binding modes for NO, right? It's linear or bend. So let's solve for this first complex. So d electrons for cobalt is how much? 9d electrons. Okay, it's d7 4s2, 3d7 4s2. So you have 9 electrons for cobalt. Okay, so d electrons are 9 plus CO, that is your carbonyl. It's a 2 electron donor. Okay, it's a 2 electron donor. You can understand this thing with molecular orbital theory. So it's a 2 electron donor. Okay, so you have 3 carbonyls over here. So what you can write down, 2 into 3. Okay, plus X is equals to 18, right? Plus X is equals to 18. So basically 9 plus 6 plus X is equals to 18. Okay, so it's 15. X is equals to 3. So if X is equals to 3, which means that this NO is a 3 electron donor, right? And 3 electron donor NO are basically binds linearly. Okay, it binds in linear fashion. Okay, this binds in linear fashion. So you have linear and linear in first and third option. Okay, so you can cancel out option number B and option number D. Okay, so you can do that for option number A, right? B and D. Now you have to figure out for third this complex. Okay, so it's nickel. How many d electrons we have in nickel? We have 10 d electrons. Okay, and it's eta 5 Cp. Okay, it's eta 5 Cp. That means heptacity is 5 for this ligand. Okay, so you can write down 5 over here, plus X is equals to 18. Okay, so again X is coming as 3, so which is also a 3 electron donor. So that means it binds in linear fashion. Okay, so correct answer is option number C. Is it clear? Right, I hope this point is clear to all of you. Lavina, d electrons are not 8, they are 10. Okay, so in this organometallics compound, what you have to consider, you have to consider s orbital electrons also, right? Basically you need vacant s orbital, so you have to consider s orbital electrons also, right? So what you can have in organometallic compounds, if the system is octahedral, it can go d2sp3, or it can just form sp3d2. That means you need vacant s orbital, so you have to consider s orbital electrons also, right? So this is nickel is d8 s2 system, so this one is d8 system and s2, so total d electrons are 10. Okay, 8 plus 2 is equals to 10, right? That's how you have to count the d electrons. Okay, let's take next question, and this is your next question. Okay, see, which of the following molecules is expected to exhibit diamagnetic behavior? Okay, so let's solve for N2. So we know this concept that in N2 we have 6 electrons, okay, and we have sp mixing also. So that's how we are going to draw MOD diagram. Okay, so 6 electrons are like this: 1, 2, 3, 4, 5, 6. Okay, so this one is diamagnetic in nature. Okay, this is diamagnetic in nature. In O2 we don't have sp mixing, so 1, 2, 3, 4 like this. Okay, so basically this is how we can fill up these electrons like this. So this one is paramagnetic in nature. Okay, so if this is paramagnetic, so S2 is also paramagnetic. Okay, because you have oxygen and sulfur. Okay, so if oxygen is paramagnetic, so definitely S2 will also form paramagnetic molecular orbital diagram. Okay, so you can cancel out option B and C. Then you have C2, right? So basically in this case also you have sp mixing, so that's how you're going to draw MOD diagram. So how many electrons you have to fill? P2, right? You have to fill 4 electrons. So 1, 2, 3, 4. Okay, it's also diamagnetic in nature. So correct options are option A and option D. Okay, so that's how you have to think it, and it's MSQ question, not MCQ. Okay, great. So let's take next question now. Which of the following combinations of atomic orbitals suggest non-bonding combinations of atomic orbitals? So we have already discussed these all concepts in detailed fashion in plus courses. If you also wish to just join plus courses and you want to revise for IIT JAM 2021 or even for 2022, you can use this referral code for Unacademy plus subscription. Okay, this referral code will give you 10% discount on your plus subscription, and you can join to live classes of all educators in IIT JAM category. Which of the following combinations of atomic orbitals suggest non-bonding combinations? Okay, in question it's saying which one of the following, but it's MSQ question. Okay, maybe there is some mistake in this question, but yes, it's MSQ question. You can see option A and D are the correct options. Okay, so yeah, which are of these followings, right, molecule is expected to exhibit diamagnetic character? Okay, great. So let's take this question now. Okay, see what we can observe over here, that this is positive and this is positive, and it's constructive overlapping. Okay, this part is constructive overlapping, so this one is allowed. Okay, what you can say, it's bonding molecular orbital. Okay, this one is bonding molecular orbital. Okay, what about this system? This is also positive, this is also positive, so constructive overlapping. This is negative and this is negative, so constructive overlapping. Okay, this is also bonding molecular orbital, right? In this case, what you have to think, this one is positive, right? This is your positive overlapping part, right? This is your positive overlapping part, and this one is negative overlapping part. Okay, so this one is constructive overlapping and this part is destructive overlapping. Okay, so basically constructive overlapping and destructive overlapping cancels out each other, so what we can say, this is a non-bonding molecular orbital theory. Okay, non-bonding molecular orbital, this one is non-bonding combination. Okay, this is not bonding combination or anti-bonding combination. Okay, similarly in this case you have this plus system and you have negative system, so this cancels out each other, right? The magnitude cancels out, so this is also non-bonding molecular orbital. Okay, so option C and option D are your correct options. Okay, option C and option D are your correct options. Okay, I hope it's clear to all of you. Let's take next question now. So these all questions are very famous in JAM level, so it's basic, it's favorites of JAM examination. So you have to just hold a good command on these homodiatomic nuclear molecules. Okay, that's why I'm taking a lot of questions, so that these all molecular orbital diagrams should be in your tips. Okay, how you have to solve these questions. For antibonding, Rajendra, you should have this destructive overlapping. Okay, magnitude of destructive overlapping should be greater than magnitude of constructive overlapping. Then you can form antibonding molecular orbital, right? But when your magnitude of destructive overlapping is equals to magnitude of constructive overlapping, in this case you'll be getting non-bonding molecular orbital, right? When your constructive overlapping magnitude is greater than destructive overlapping magnitude, then this is a case of bonding molecular orbital, right? Is it clear? Is it clear to all of you? Okay, great. Okay, in which of the following ionization processes the bond order has increased and the magnetic behavior has changed? Okay, see, in this case, tell me bond order has increased or it has decreased. When you are going from N2 to N2 positive, that means you are taking electron from bonding molecular orbital. Okay, you are taking electron from bonding molecular orbital, so definitely bond order should decrease. Okay, it should decrease, so this is not the correct option. Okay, next is from C2 to C2 positive. Again, you have electrons in bonding molecular orbital. So when you are taking electrons from bonding molecular orbital, bond order should decrease, right? So this is not the correct option. Okay. In this case, you have NO and NO positive. Okay. So you have one unpaired electron in pi star. Okay, you have one unpaired electron in pi star. So if you are taking electron from anti-bonding molecular orbital, then bond order should increase. Okay, it should increase, and the magnetic behavior has changed. So it was paramagnetic. Now when we have eliminated this one electron, now it's going to be diamagnetic. Okay, so there is change in this magnetic behavior also, and bond order also has increased. Okay, so correct option is option number C. Okay, when you are taking electrons from O2 to O2 positive. Okay, so when you are taking electrons from O2, this is your O2. So in this case you are taking electrons from anti-bonding molecular orbital, so bond order is increasing for sure, but magnetic behavior will remain same. Okay, it is this was paramagnetic, and after elimination of one electron, right, it will be paramagnetic only, right? So there is no change of magnetic behavior. So what I can say, that option number C is the most right plausible answer over here. Okay, yeah, in both it will increase, but the magnetic behavior won't change. Okay, you have to consider both the statements, right, Shruti? You have to consider both the statements. Okay, so we have to consider both the statements. So if I consider both statements, option C is the most correct answer. Okay, let's take next question now. Okay, so in option number fifth, right, this is positive and positive. So this one is constructive overlapping, and this is negative and negative. This is also constructive overlapping. So it's a two-lobe interaction which is allowed. Okay, two-lobe interaction is allowed. It will give you pi. So basically these are two constructive overlapping. So this one is allowed. Okay, in option 4 it's a one lobe interaction. Okay, one lobe interaction, and positive, this is a constructive interference part. Okay, so this one is also allowed. Then in option 3, what you are observing, this one is destructive. Okay, this is also destructive, so it's not allowed. Okay, it's not allowed. This one is destructive and destructive. Okay, so in this particular case this is also not allowed, right? It's a constructive overlapping, but this is not the correct orientation. Okay, so pi bonds, p orbitals will approach like head to head, or they will approach like sideways overlapping. Okay, this is not the correct orientation for formation of bond. Okay, so this is incorrect option over here. This is not allowed, right? And this is not allowed. Let's go to option first. So this is not one lobe interaction or two lobe interaction. Okay, so this way also it's not allowed, right? This way also it's not allowed. It will give you non-bonding positive and negative, so these will cancel out each other. Okay, so correct answer is option number second, right? This is your correct answer. Okay, yes, combination is not linear, right? Very good, somehow it's not linear. Okay, so theory says this is basically coming from LCAO model. Okay, linear combination of atomic orbitals. Okay, linear combination of atomic orbitals, they should combine linearly. Okay, so they should come on a particular axis. Okay, you have to just right, you have to approach these molecular orbitals in a particular axis. Okay, see, they are approaching in incorrect axis. Okay, it's not correct way to just form molecular orbitals, so this is not the correct option. Okay, so option second is the correct answer for this option. Okay, let's take next question now, and I think we have discussed this question, so let's take next one. Okay, third one, right? Yes, it forms anti-bonding molecular orbital, right? It's form anti-bonding molecular orbital, right? It forms anti-bonding molecular orbital. See, okay, if I go by the concept, then we can get anti-bonding molecular orbital, right? But if I just go with the options, so there is no such option like 1 and 2. Okay, there is no such option like 1 and 2. So what I have to select, I have to select second option, right? Is it clear? I have to select second option, because right, there is no such option in which I have 1 and 2. Okay, so we have to go with options, right? That's the best way to approach the questions. If you have options, you should take advantages of having the options. Okay, no, non-bonding is not allowed. Okay, non-bonding is not allowed. It's basically your your atomic orbitals only, right? So non-bonding is not allowed. Okay, so basically the question is the increasing order of the observed infrared stretching frequency of carbonyl, okay, among the following isoelectronic complexes. Okay, isoelectronic means d electrons are same in all these complexes. Okay, so now we have to tell the order for stretching frequency. Okay, so what is stretching frequency? Stretching frequency is 1 by 2 pi c under root k by mu. Okay, so that means your reduced mass is same. So what I can say that the stretching frequency is directly proportional to under root of k. Okay, this one is directly proportional to under root of k. That means force constant. Okay, so if I increase this charges on this complexes, okay, see, from positive you have zero charge and you have negative charge. If your metal is having negative charge, that means the electron density is high, right? So it's going to donate back to this carbonyl, right? It's going to donate back to this carbonyl. Now if I draw molecular orbital diagram of carbonyl, what I'll observe that I have this empty pi star. Okay, empty pi star, so it will accept this electron density in pi star, which is anti-bonding molecular orbital, right? So whenever you add electron density in anti-bonding molecular orbital, so your basically back bonding is increased. Okay, if back bonding is increased, so what can I say? Bond strength is decreased. Okay, bond strength is decreased, or what I can say that stretching frequency will definitely decrease, because stretching frequency is directly proportional to your bond strength. Okay, so now if I just compare these three metals, so I have V negative, basically oxidation state is V negative, you have chromium and you have Mn positive. Okay, in this case back bonding will be least, so that means stretching frequency will be maximum. Okay, stretching frequency will be maximum in first option. So that's how you have to go with this, right, question. Okay, that's how you have to go with this particular option, and I hope it's clear to all of you, right? Is it clear, guys? Is it clear to all of you, right? Okay, let's take next question now, and this is your next question. No, basically the concept over here is, see, what is this isoelectronic system? Let me tell you, right? Just give me a second. Okay, so you have V negative, okay, and you have Cr and you have Mn positive, okay. So it's your 3d5 and s2 system, right? So that means how many electrons you have? 7. Now if you have this system, so you have 6 electrons. Okay, you have 6 electrons over here also, and similarly you have 6 electrons over here also, right? So now back bonding is dependent on this oxidation state. Okay, that means oxidation state is negative, so it will donate more. If it will donate more, so definitely back bonding is going to increase over here, right? Okay, okay, just let's explain this question again. Okay, just give me a second. See, what is happening over here in this case, what you have to see, so basically oxidation state is negative on vanadium, then you have chromium at 0 oxidation state, then you have manganese at +1 oxidation state. Okay, so you need to find out the back bonding extent. Okay, so if your negative oxidation state is increasing, that means your this electron density on metal is increasing, right? If electron density on metal is increasing, so what will happen? It will donate to this carbonyl, right? It will donate more electron density to this carbonyl. Can I say that, Shilpi? It will donate more electron density to this carbonyl. Okay, so what's going to happen? So carbonyl is going to accept this electron density in pi star. Okay, it's going to accept this electron density in pi star. So if you are clear with MOD diagram of carbonyl, you will get this concept that it's going to accept electron density in pi star. Now whenever you are adding electrons and antibonding molecular orbitals, so bond order decreases, okay, or bond strength decreases, right? If bond order is decreasing or bond strength is decreasing, that means stretching frequency, which is directly proportional to under root of k, which is directly proportional to bond strength. If it's directly proportional to bond strength and your bond strength is decreasing, that means your stretching frequency will decrease. Okay, it will automatically decrease. So in this case, you have Mn positive. That means the extent of back bonding will be least in this complex. Okay, so it's going to have maximum stretching frequency. Then you have this complex, then you have this complex. Okay, I hope it's clear, right? Okay, let's take next question now. Is it clear now, Shilpi? Just tell me. Okay, so 30 more seconds for this question. It's a good question. So 30 more seconds, then we'll be discussing this question. Okay, so basically the question is complexes of journal formula. It's a facial isomer MoCO3 phosphine 3. So you have this type of complex Ma3B3. Okay, it's a facial isomer, have the CO stretching frequency bands. Okay, so basically you have to match these stretching frequency when you have these phosphine ligands. Okay, you have these derivatives of phosphine ligands. What is phosphine? Phosphine is pH3. Okay, so these are also called as phosphines or derivatives of phosphines. Okay, so what we have to do now, see, it's a question from whenever you have side auxiliary ligands. Okay, so in this case these ligands are auxiliary ligands, right, or spectator ligands, right? They are spectator or auxiliary ligands. Okay, so now how this is going to affect your stretching frequency of carbonyl, that we have to see. Okay, so let's take these all complexes. Okay, for that we need to first arrange the correct order of pi acceptor ligands. Okay, we should know that all these phosphine ligands are pi acceptor in nature. Okay, all these ligands are pi acceptor in nature. Basically they are not accepting the electrons in pi star, but they are accepting in sigma star, but sigma star is very low lying, so we can call these ligands as pi acceptor ligands. Okay, so all these ligands are your pi acceptor ligands. So what we need to do, we need to arrange them in correct order of pi accepting tendency. Okay, so let's take A, B, C, D. Now you guys tell me what's the correct order of pi accepting tendency when you have A as this PF3, B is PCl3, then C is when you have phosphorus chlorine which is attached to two phenyl rings, then you have PME3. Okay, just tell me the decreasing order of pi acceptor ligands. Just tell me decreasing order of pi accepting tendency of these ligands. All of you just quickly tell me in the comment section that what's going to be a decreasing order of pi accepting tendency of these phosphine ligands. It's all right. It's a concept from organometallics. Okay, so it's a concept from organometallics. If you are present on Plus platform, you can attend the courses. Okay, I have discussed this in detail, that how we can just discuss this concept. Okay, I'll be discussing again this concept in organometallics, but definitely if I have discussed this in molecular orbital theory, so we can do these questions. Okay, just tell me what's the tendency, what's the order of pi accepting tendency of these phosphine ligands. Come on guys, quickly, those who are present live in this session. Right, okay. So basically the order is PF3 being strongest pi acceptor ligand, then you have PCl3, then you have PCl, PH2, then you have PME3. Okay, so this is the order of pi acceptor ligands. Okay, well done guys. PF3, PCl3, PCl, PPH2, and you have PME3. Okay, if this is the order of pi accepting tendency, so what can I say? Basically, what's the concept over here? If these are better pi acceptor ligands, so this metal, okay, this metal is going to donate electrons to these pi acceptor ligands. Okay, so this metal is going to donate electrons to these pi acceptor ligands. So what can I say? That back bonding in carbonyl will decrease. Okay, because you have more pi acceptor ligands present in the complex, so it's going to donate to these pi acceptor ligands also and to carbonyls also, right? But you have increased this pi acceptor tendency, so that means they are now going to donate electrons to these pi acceptor ligands. So back bonding in this carbonyls will be decreased. If back bonding is decreased, that means you are not adding electrons and anti-bonding, so eventually your stretching frequency will increase. Okay, so whenever you have strongest pi acceptor ligands, so you're going to observe maximum stretching frequency of carbonyl. Okay, maximum stretching frequency of carbonyl. Okay, so that means PF3 2090 is the maximum stretching frequency. So you'll get the stretching frequency whenever you have PF3 as phosphine ligand. Okay, because it's a good pi acceptor ligand, so what will happen? Back bonding in carbonyls will decrease, and if back bonding is decreased, so bond order will increase or bond strength will increase, and you will observe maximum stretching frequency. Okay, so for PF3 you have 2090, so A, right? This is going to be a correct answer. So there is no need to check rest of the options, but still we can do that. Okay, this is next and this is next, and then you'll be observing this. Okay, so correct answer is option number A. It's a good question, right? If you're clear with the concept, you can solve it in within seconds. Okay, it's a very easy question, right? So let's take next question now. Again, a very simple question. Which one of the following have been arranged in increasing order of bond order as well as bond dissociation energy? Yes, back bonding will be there, right? Definitely it's going to be there, but the direction will be now inclined towards your this auxiliary pi acceptor ligands. Okay, not carbonyl. The extent of back bonding in carbonyl will decrease if you're adding more and more pi acceptor ligands. Okay, okay, see, in this case, Soumya, what we have to see, Soumya Ranjan, let's say, okay, if you have C option as PPH3, okay, and D option as PME3, right? So this is good pi acceptor ligand. This is the order of pi acceptor ligand. Okay, so PPH3 is a better pi acceptor ligand. Okay, then PME3, so order will remain same. Okay, order is going to remain same if you have these type of ligands. Okay, See, let me tell you the correct pi acceptor order. Okay. See, the pi acceptor order is you have PF3, then you have PCl3, okay, then you have PBr3, then you have PI3, and what you can write next, you can write down POPH3, okay, then you can write down POR3, okay, then you can write down PPH3, okay, then you can write down PR3, then you can write down PH3, right? This is the pi acceptor order of these phosphine derivatives, okay. Is it clear to all of you? Is it clear? PPH3, you will have PCl3, PBr3, PI3, POPH3, POR3, PPH3, and then you'll have PR3 and PH3, okay. This is your pi acceptor order. Okay, see, the reason is very obvious. These are electronegative elements, so F3, then Cl3, Br3 and I3, so it's going to increase electrophilicity on this phosphorus. So what will happen? Electronegativity of this phosphorus will increase. If electronegativity is increased, that means these energy levels will be reduced. If energy levels will be reduced, so the electron accepting tendency will be increased. Okay, that's the reason over here. Then this is O, right? So oxygen is right. Okay, yeah, so oxygen is your more electronegative element, so that's why it's coming right after this iodine. Then you have OPH3 and OR3. So how are you going to differentiate between OPH3 and OR3? So basically phosphine, okay, basically it's pH ligand phenyl ring, which is also having minus I effect. Okay, so you have to consider inductive effect over here, which will increase the electronegativity of phosphorus. Okay, then you have POR3, then you have PPH3, PR3 and PH3. Okay, that's your pi acceptor tendency. Okay, I think we have some more questions. It will go by half an hour. Okay, we'll take half an hour more, Asha, for this session to complete. Okay, now let's solve this question. No, electronegativity we have to consider. Okay, these all ligands will have good electronegativity, so you have to consider, right, because you have minus I effect, and if you compare minus I effect of halogen, so it's like dominating. Okay, so you have to see that characters also, and for that you need to see molecular orbital diagrams also, right? Okay, yeah, so when you are in just taking electrons from oxygen, that means you are taking electrons from antibonding, so you're increasing bond order as well as bond dissociation energy, right? So bond order is directly proportional to bond dissociation energy, right? Bond order is directly proportional to bond dissociation energy. So O2 positive, O2, O2 negative, O2, 2 negative, because in this way you are increasing electrons in antibonding. Okay, so if you are increasing electrons in antibonding, that means you are decreasing bond order and you are decreasing bond strength. Okay, in this way, in this direction. All right, so correct answer is option number B. Ionization, okay. O2 positive and O2 negative. Okay, this is your question. What's your question? O2 positive and O2 negative. You are confusing between this O2 positive and O2 negative. How we can find out the ionization energy? This is your question. Just confirm it so that we can discuss it. Okay. Let's take next question. Among the following, the paramagnetic compound is. Okay, so O2 positive, O2 negative. Okay, O2 positive means you have this one electron over here. Okay, O2 negative means you have these electrons. Okay, so what you can say over here, basically what you have to see, in this case you have more electrons in antibonding. Okay, If you have more electrons in antibonding, that means bond strength is less or stability is less. Okay, so it's going to lose this electron very easily. That's a favorable process. So ionization energy will be O2 positive greater than O2 negative. This is the first way to explain this concept. Second way is O2 positive means you have positive charge, so En value is higher. If En value is more, so that means it's difficult for us to take electron from isolated gaseous atom. Okay, so again we can write down O2 positive is greater than O2 negative. Is it clear now? Rajendra, is it clear how we got this order of ionization energy? Okay, great. So this one is O2, 2 negative, peroxide form. This is ozone. This is your normal oxide form. Okay, and this is your superoxide form. Okay, among the following, the paramagnetic compound. Okay, so this one is not paramagnetic because you have two electrons. You have added two more electrons. It's going to be diamagnetic. Okay, ozone is also diamagnetic. Okay, it's also diamagnetic. You can just draw the structures. And this one is oxide. So what you can see, okay, how many electrons you have in oxide? Okay, basically you have 8 electrons. Okay, if you have 8 electrons, you have added 2 more electrons, so it's going to be like this. Okay, you have 4 electrons in P, so you have added 2 more electrons, so it's paramagnetic. Okay, it's diamagnetic in nature. Okay, next is your superoxide form. So you have eliminated one electron, so you have one more electron, one unpaired electron in this pi star. So what you can say, it's your paramagnetic. Okay, so correct answer is option number D. Good work, guys. Okay, let's take next question now. No, we don't need MO of ozone in previous question. Okay, just you can go with VBT theory or you can go with Lewis structure. Okay, you'll get the correct answer. Okay, let's start solving this question. So we need to find out isoelectronic systems. Okay, first we need to check that these NO will behave as one electron donor or three electron donor. Okay, that we need to check. So we know it's chromium, right? So it's 4. That means it's going to follow 18 electron system. You have manganese, Again it's 4, so tetrahedral system, 18 electron system. It's cobalt, so tetrahedral system, 18 electron system, and iron, it's going to follow 18 electron system. Okay, so that means what we need to check, that this NO is your linear. Okay, this NO is your linear, that we need to check over here, right? So in all these compounds, this NO will behave as linear. Okay, so let's find out this question. So you have chromium NO4. Okay, if it's linear, chromium will have 6 electrons. Okay, 6 plus 4 into 3. Okay, 12 plus 6 is equals to 18. So it will follow 18 electron system. That's why this NO is your linear. Okay, second is cobalt. You have 9 electrons. So 3 into 3. Okay, basically it's 9. 9 plus 9 is equals to 18. Okay, manganese will have 7 electrons plus 2 electrons plus 9 electrons. Okay, 3 into 3, it's 9, so it's also following 18 electron system. Okay, then you have 8 electrons plus 4 electrons plus 6 electrons. Okay, so this is also 18. That means correct answer is all. Okay, because all these compounds are giving you 18 electron system, so they are isoelectronic. Okay, they are isoelectronic, they have same number of electrons. Okay, so correct answer is option number D. Okay. Okay, in 5 seconds, just tell me the correct answer. Okay, you have 5 seconds. Just tell me the correct answer. Which of the following species exhibit the diamagnetic behavior? Okay, within 5 seconds, you have to tell the correct answer. Okay, you don't have time more than 5 seconds. So just tell me which one of the following will exhibit diamagnetic behavior. Can I say O2 2 negative without writing molecular orbital diagram? Can I say that? Right? O2 2 negative. Okay, great. So O2 2 negative, because you have two unpaired electrons, it's going to capture two more electrons. It will be diamagnetic. Okay, this is going to be paramagnetic. This is also paramagnetic. This is also paramagnetic. Okay, right. So these all questions should be on your tips. Okay, how we have to solve this question. Okay, good work, guys. Let's take next question. Which one of the following pairs of species has the same bond order? Great. So basically, they are asking for isoelectronic pairs. Okay. Now, what is isoelectronic pairs? Right? You should have bond order same. Okay. So those compounds which have bond or same bond order, those compounds are isoelectronic pairs. Okay. So what we need to understand: N2, Cn negative, NO positive, CO. Right? These four are isoelectronic compounds, or they have same bond order, that is 3. Okay, so basically you have 3 bond order for all these 4 compounds. Okay, or molecules. So correct answer is option number A. Okay, correct one is option number A. Great. Let's take next question. Assuming 2s 2p mixing is not operative, the paramagnetic species among the following is. right? So this is how we can draw molecular orbital diagram. So if 2s2p mixing is not operative, then C2 is going to have paramagnetic character. Okay, you'll have two unpaired electrons over here, right? You'll be getting two unpaired electrons over here. So correct answer is option number C. Okay, correct one is option number C. I hope it's clear to all of you. So let's take next question now. Great. Okay. So in bonding molecular orbital of MO of hydrogen, electron density is increased between the nucleus. Yes, definitely that's the correct thing. See how it's going to increase. Let's see that. Okay. See. Okay, one second. Right. Yeah. So let's suppose this is your 1s orbital, okay, and this is your 1s orbital of your hydrogen, okay. So what you have to see, this is your 1s orbital of hydrogen. So it's like this format, okay. This is your format of 1s orbital and this is your wave density of 1s orbital, okay. Now what's going to happen whenever you combine these two wave functions, you'll be getting something like this, okay. That means electron density is increased, right? It's increased right around this particular nucleus, okay. Electron density is increased around this particular nucleus. So correct statement is 1, okay. Statement 1 is definitely your correct statement. The bonding MO is phi A plus phi B, which shows destructive interference. So bonding MO is formed due to constructive interference, not destructive interference, okay, of the combining electron waves. So statement 2 is incorrect statement and it's not the explanation of first statement, okay. See, option C is definitely correct option, okay. Statement 1 is correct and statement 2 is incorrect, okay. That's how you have to think of this question, okay. Good work, guys. Let's take next question. Again a very simple question. So you'll see a lot of previous year questions from this homodiatomic molecule, okay. So just they have reframed the question in a different format, but the question concept is simple, right? Which of the following molecules ions does not contain unpaired electron, okay. Which of the following molecules and ions does not contain unpaired electron, that you have to tell me. Again, correct answer will be option number A, right? We have discussed this question. In that sense, we have to tell the diamagnetic behavior, okay? And this case also, it does not contain unpaired electron, okay? So A is going to be your answer, okay? Let's take next question now. Okay. So, which of the following overlaps is or are incorrect, assuming x-axis to be the internuclear axis? Okay, let's assume that this is our internuclear axis x. Okay, so if you have x-axis, so you have 2py and 2py. So let's take 2py like this and 2py like this. Okay, so it's a two-lobe interaction. So yes, we can say there's a possibility of getting pi bond over here. So option A is correct. Okay. Then you have x-axis, so 2pz, let's suppose you have 2pz like this and 2pz like this. Okay, so it's a two lobe interaction, so there's a possibility to get pi and pi star but not sigma bond. Okay, so option B is incorrect. Let's go to third option. So you have x-axis, 2px and 2px, so you have x-axis, so it's 2px like this, 2px like this, right? So it's a one lobe interaction, so there's a possibility to get sigma or sigma star. Okay, pi is not possible, so C is also incorrect. Okay, then you have D. So in D, if this is your x-axis, so let's suppose this is 1s and this is your 2py. Okay, this is your 2py, so there's not a possibility to get pi bond, even it's non-bonding, right? It's non-bonding. If it's positive, so it will cancel out, so this is going to be your non-bonding molecular orbital. Okay, so this is also incorrect. Then you have E option. This is your x-axis, 2py. Okay, let's suppose this is 2py and 2pz. Okay, so this is also non-bonding. Okay, this is also incorrect option. Then you have 1s and 2s. Okay, so yes, these two can overlap and you can get sigma bond. Okay, so this is correct. So option B is incorrect, option C is incorrect, option D is incorrect, and option E is incorrect. Okay, so basically four options are your incorrect statement. Okay, I hope this one is clear. Let's take next question. Comment on stability of these three ions. You have to arrange them in decreasing order of stability. Okay. See, in this case, bond order is 1. Okay. In this case, bond order is 0.5, right? And in this case, bond order is also 0.5. Okay. So what we can say, if we want to write down the order of bond order, decreasing bond order, so it will be H2, then H2 positive is equals to H2 negative. But here we have to comment on stability of these three molecules. Okay. So if we want to compare the stability, so definitely bond order 1 will be more stable. Then in this H2 positive and H2 negative, this is going to be your least stable because you have more electrons in antibonding, right? Yes, bond order is same, but you have more electrons in antibonding. So correct order will be H2 positive and H2 negative, right? This is going to be your correct order. I hope it's clear. Let's take next question. The infrared stretching frequency of carbonyl bonds of PR follow the order. The question is, you have to tell the correct order of stretching frequency. Okay, you have to tell the correct order of stretching frequency of these complexes, right? So you have carbonyl positive charge, you have carbonyl this complex positive charge. Okay, you have to arrange them in decreasing order of stretching frequency. Why you're giving the incorrect answers? I have discussed this question in class also, right? Yeah, I'll explain it. Okay, I'll explain it, Abhilasha. I have discussed this concept already in class. So let's discuss this concept. Basically, what's the question? You have carbonyl positive, and you have this metal complex. Okay, so when you have carbonyl, so that means, right, it's a pure. Okay, you have carbonyl positive, so that means you have eliminated the lone pairs of electron, which is a non-bonding, which is slight anti-bonding character. Okay, so basically this is your homo for carbonyl, and this is your non-bonding, which is slight anti-bonding characters. Okay, so it's the permanent loss of electrons. Okay, so you have eliminated these electrons. So can I say bond order will increase of carbonyl? Yes, definitely it will increase, because this non-bonding will have right, it's actually having anti-bonding characters. So if you are eliminating electrons from anti-bonding, so definitely your bond order is going to increase. Okay, so that means bond order will definitely increase. And if bond order will increase, so I can say stretching frequency will increase in comparison with this CO. Okay, this neutral CO. So that means CO plus will have more stretching frequency than CO. So this can be your answer. This can be your answer. You can cancel out this option, and you can cancel out this option, right? So these two options we can definitely cancel out. Okay, now we have to compare between metal and these two complexes. Okay, so whenever you are just taking one metal complex, okay, and you have CO plus and you have CO, so what I can say, see, in this case you will have carbon monoxide. Okay, you will have metal. So this carbon monoxide is going to donate this lone pair of electrons from antibonding, which is slight antibonding characters, to this this vacant d orbital. Okay, it's going to donate like this in this direction. Then what will happen? This metal will definitely have filled d orbitals like this. Okay, it will definitely have filled d orbitals, and these carbon and oxide will have this right pi star. Okay, vacant pi star, so these are vacant pi stars, so it will just donate back this electron density. Okay, so it will donate by this sigma bond and accept by this pi bond. Okay, so what I can say that it's a bidirectional, right, it's a bidirection, so what I can say, it's a pi acceptor ligand. Okay, carbonyl is a pi acceptor ligand. So basically, yes, synergic back bonding. So whenever you have carbonyl complexes with metal, so that means there's a criteria of back bonding. If there's a criteria of back bonding, so that means you are adding electrons to pure anti-bonding now. Right? Pi star is your pure anti-bonding. That means you're adding electrons to pure anti-bonding. Right? So that means your stretching frequency is going to decrease. Okay? So correct answer is option number A. Is it clear to all of you? Abhilasha, is it clear? Shruti, is it clear? Those of you who went with option C, Aruna, is it clear? Soumya, is it clear? Right? Ashlata, is it clear? Kishore, all of you are clear with this concept that how option A is the correct answer, right? So whenever you see these type of complexes, you always have to put metal complex in end, okay? Because it's going to have back bonding, which will reduce stretching frequency because you are adding electrons in pure anti-bonding. Right, you are taking it from non-bonding, which is slight anti-bonding characters, but you are adding into pure anti-bonding. Okay, so that means it will decrease by a larger extent. Okay, great. So let's take next question now. See, Surinder, right, we have to be practical. So now we have, right, only 2 months, okay? To be very honest, you have only December and January, okay? So if you have been preparing from past months, or what I can say, if you are preparing this exam or your basics are clear, then yes, we can think of clearing jam examination, right? But if your basics are not clear, then definitely you need more time. Okay, if your basics are clear, your 12th standard basics, your BSc basics are clear, right? You don't need basic definitions, so yes, we can crack it. But if your basics are not clear, so you need more time. Okay, at least if your basics are not clear, at least you need 6 months preparation, right? Or we can say 4 to 6 months preparation if your basics are not clear, right? But if your basics are clear, yes, you can crack examination in 2 months. Okay, you can do that in 2 months if your basics are clear. Okay, if you have any more thing to discuss, you want me to write, basically you want any discussion on this IIT JAM preparation, so you can just message me on Unacademy. Okay, go to my profile, you'll find the link in description box, or you have link of Telegram channel, you can just message me over there, right? I'll definitely guide you. If your basics are clear, we can think of clearing this JAM examination in 2 months. Okay. Okay, so number of and type of bonds between two carbons in calcium carbide. Okay, number and type of bonds between two carbon atoms in calcium carbide. Okay, so basically calcium carbide is like this. Okay, so you have to draw C2, then you have to add 2 more electrons to it. Okay, so if I draw molecular orbital diagram of C2, so there is sp mixing in C2, so you have to draw a molecular orbital diagram like this. Okay, 1 and 2 electrons over here. Basically you have to fill 4 electrons, then you are adding 2 more electrons like this. Okay, so basically what you have 2 pi bonds. Okay, see, one pi bond, second pi bond, and one sigma bond. Okay, so 2 pi bonds and one sigma bond. Okay, you have 2 pi bonds and one sigma bond, so B is the correct option. Okay, B is the correct answer. 1 sigma and 2 pi bonds. Okay, let's take next question now. So you have to tell oxidation state of Ru in this complex. Okay, see, inorganic, organic, and physical, all three will have same weightage. Okay, you'll get 33% of inorganic, 33% of organic, and 33% of physical. Okay, right, so basically you have to prepare all three subjects. Okay, you cannot leave any one subject, all three will have same weightage. Okay, so let's do this question, oxidation state of Ru in this complex. Okay, the complex is RuPPH3 ClNO, right? This is your complex. Okay, see, what we have to find out, first of all, this is ruthenium complex. Okay, and steric number is equals to 4, right? It's a Ru complex and steric number is equals to 4. Okay, so what's geometry of this complex? Anyone? If steric number is 4, so you can have square, planar, or tetrahedral. Okay, so just can you tell me, is it a square planar complex or tetrahedral? Ru will definitely form square planar complexes, right? It's going to form Z exclusion type of geometries. Can I say that? Right? It's going to form Z exclusion type of geometry. So that means it's a square planar complex, and square planar complexes and square pyramidal complexes generally follow 16 electron rule. Okay, it generally follows 16 electron rule. So Ru, it comes in iron family. Okay, ferrous, right? So you have 8 electrons for Ru. Then ppH3 is a 2 electron donor, 2 into 2 4. Then chlorine is a 1 electron donor, and NOx is equals to 16. Okay, that means first of all you need to find out the binding of this X. Okay, so it's 12 and 1 13 and 16, so X is equals to 3. That means here NO is a 3 electron donor, right? If NO is a 3 electron donor, so charge on NO will be NO positive. right? It's a 3 electron donor. So charge on NO will be NO positive, right? So what we have to find over here, we need to find out oxidation state. Now that means your complex is PPH3 whole twice Cl and NO, right? X, let's suppose X is the oxidation state of Ru. PPH3 is a neutral ligand, so -1 for chlorine and +1 for NO is equals to 0. So -1 and +1 cancels out. So X is equals to 0. That means Ru is in zero oxidation state, right? So correct answer over here is option number B, right? Option B is your correct answer. I hope this is clear to all of you. Let's take next question, and this is Z minus, this is metal carbonyl and X. Okay, this is X and this is Z minus. So this is the last question. So I want all of you to give the correct answers. Okay, so please give your best shot and give the correct answer. Okay, so very easy question this one. So you have to just tell the correct answer, the correct combination of metal, number of carbonyl ligands, and the charge for a metal carbonyl complex that satisfies the 18 electron rule. Okay, the question is very simple. Okay, just use hit and trial method. That means you have to use options. Okay, that's all. Okay, let's start with option A. Okay, titanium. So scandium, titanium. So it's a 3d2 4s2. So it's a 4 electron system. Then let's say X is equals to 6, that means 12. Okay, and it's minus charge -1, so you have to add this charge. Okay, so 14 plus 12 plus 4 is 16 is equals to 17. So this is a 17 electron system. So this is incorrect option. Okay, if you have cobalt, so that means 9 electrons, 8, right, plus 2. So it's a 19 electron system. So this is also incorrect option. Okay, molybdenum. So what you have to see, it's from chromium family, right? Okay, so 3d5 4s1, that means it's a 6 electron system plus 10 plus 1. So it's 17 electron system. Over here, what you have to see, scandium, titanium, vanadium. Okay, it's 3d2 4s2. So 5, 12 and plus 1. So 17 plus 1, it's a 18 electron system. Okay, so correct answer is option number B. Okay, is it clear to all of you? Correct answer is option number B. Okay, so we have discussed around 30 questions today. Okay, and let me just tell you what all you have to revise in molecular orbital theory so that you can revise this portion and you can conclude this portion now. So basically in molecular orbital theory, if I just start from very basics, so you have to study the diagrams of your, first of all you have to study LCAO method. Okay, how we can form sigma bonds, pi bonds, del bonds. Okay, these three you have to study. Then you have to go to H2, He2, right, Be2, this molecular orbital diagrams. Then you have to go to Li2, definitely, right. Then B2, these all orbitals, N2, O2, C2, right, and F2 and Ne2, right, neon 2, these two you have to definitely study. Okay, next after this thing, what you have to study in fluorine, you have to study for chlorine, bromine and iodine. Okay, this is all about homodiatomic molecule. In heterodiatomic molecule, you have to study CO, Cn negative, NO, right, you have to study these three. Then you have to study HF, HCl, HBr, Hi, ICl. Okay, these all you have to study. So yeah, I think this is all about these heterodiatomic molecule. So what, yeah, you have to study all these compounds. Then you have to study in polyatomic, you have to study BeH2, you have to study NH3, you have to study H2O, BH3. Okay, these three you have to study, and yes, H2O, right? And in this case, you have to study OH minus also, right? OH minus you have to study, and OF minus. Okay, so these all you have to study. So if you just study these all molecular orbital diagrams properly, so you can definitely right, do well in this molecular orbital questions. Okay, so these all you have to study, right? Yeah, it's important for jam, right? But the weightage is very less. So if you are struggling with your syllabus, then you can skip this portion. But if your syllabus is going good, then you can study, at least you can study titration portion. Okay, most of the question in jam are from analytical titrations only, right? Analytical titration, just like your conductometric titrations, potentiometric titration, acid base titrations, right? And you have redox titrations, then you have I think, yeah, after redox, you have this precipitation titrations and complexometric titrations. Okay, this portion you can study for IIT JAM. Okay, and basic this inorganic analysis. Okay, basic inorganic analysis of salts you can study. Okay, this much is enough for JAM. All right. So for this all molecular orbital theory, if I want to give you a particular book, so you can refer foreign authors. You can refer this Hui, right? You can refer Hui. You can refer Missler and Tar. Okay, you can refer Missler and Tar, or you can refer Shliver and Atkins. Okay, these three books are good for molecular orbital theory, and for analytical chemistry, you can refer Skoog. Okay, these two books are good for analytical chemistry. Okay, right? And Surender, if you have any doubts to ask, right? So just message me on Unacademy. Okay, in the description box you'll find my link, profile link. You just message me over there. This is my profile. You just go to my profile, you'll find a message box over there, right? So you can drop your queries over there, right? I'll definitely connect with you. Just do one thing, you drop your queries over there, right? Okay, so right, so let's end this session now. If you have any more things to discuss, you can definitely message me on Unacademy app. Okay, I'll see you guys in the next class. Keep revising your topic, right? I'll see you in the next class. Take care, everyone. Bye bye.